Oh, you should be getting like 0.015, no, 0.019, oh, 0.009 something. Where's my calculator?
Well, I might have calculated the.
Might have done something wrong.
Yeah.
Why don't we just take that value?
Oh, I know I did wrong. I subtracted one.
Oh.
Supposed to be subtracting 1.01.
Yeah, you essentially get the same concentration. It's like this 0.01. If you wanted to be accurate, it'd be 0.009995. But that's great. So now we do that, plug it in, we get the real answer of
0099. Yeah, that's good.
and then these would be the same, right? We know that this is now. There's one other little detail that needs to be addressed. So now that we understand a good approach to solving for a weak acid, this is how you have to solve for a weak acid like this every single time. Just FYI, this is how you solve for a weak acid in terms of how much is left here, what our hydronium concentration is, how much of our conjugate base is, and if you have a weak base, you just flip-flop this, and we would use a Kb, and you do the same thing. But you'd use a Kb instead of a Ka, which I probably should have pointed out. So at this point, we have a really tiny amount of dissociation.
Mm-hmm.
But in water, is there already, and this isn't a trick question, is there already hydronium or hydroxide?
Yes.
How much at 25 degrees Celsius?
I'm not sure.
I'll tell
Wait,
you.
no, I know what it is. It's 1 times 10 to the negative 7.
Good. And what is that units?
That is.
It's a trickier one.
pH.
Molarity.
Okay.
So, oh, and by the way, these are all molarity, right?
Mm-hmm.
That's important to remember, because you have to use molarity when you're using the equilibrium constant expression. So we have this much here already, right?
Mm-hmm.
So that means, oh, how much of BRO minus do we have? Kind of a trick question,
I
but
want to say the 1.0.
0.
Okay. I have it written out.
Oh, right. 0 because at the beginning, there's none of this in there. Until we stick this in there, then a little bit dissociates off, right? So we have to take this number and add it to this if the dissociation is really small. Because we have to take that into consideration because there's already a little bit of hydronium in the water, and that's tiny, right? That's 1.0 times 10 to the negative 7, right? So if we have that much hydronium, and then we stick in a strong acid, well, it's going to be like a perfect one-to-one dissociation. Like it'll dissociate completely, and you'll be left, however much strong acid you put in there will be how many moles of hydronium you have. Does that make sense?
Mm-hmm.
But if you have a weak that hardly dissociates, that means that the hydronium concentration that exists there already is going to be an important factor to add to how much it dissociated. So if this is a really tiny number, which it is, you take this and this together, which just makes it 4.896.
Okay.
Because this number times that number is that. Because it's just one more decimal over, right?
Mm-hmm.
Um,
So it's not necessarily if the original concentration was small. It's if the equilibrium concentration is small.
it's if the amount of dissociation from the original acid here is really small. So if you solve for x and your x value is really, really small, if it's close to this number at all, you will need to put that into, you'll need to take that into account. Because there'll be times when you solve for x and it's like times 10 to the negative 8. That's a basic solution if you think about it. But if you add this to this, then you'll end up getting 1.1 times 10 to the negative 7, right? Which is slightly on the acidic side. Like that's like a pH of 6.9 or 8 or something. Like it's really not very acidic. But that's important to remember. That's on sapling. I don't know if you've done that already.
And I appreciate that.
Oh, you need to go.
I wouldn't have figured it. I wouldn't have realized that it was
Important.
Well, I thought it was like the smaller concentration of this. If this is a small concentration, but it's if X is a small concentration.
Yes.
Then we add this.
Mm-hmm.
Okay.
As a matter of fact, when you're saying all the time, if you go, oh, how much do we have? Oh, 0 and 0. You're actually saying approximately 0 for this. Because there's always some 1.0 times 10 to the negative 7. There's always that much. But notice that's only for 25 degrees Celsius. If you change the temperature, that number changes. But we'll talk about that later.
Okay, cool. I appreciate that. That was gold. What we talked about, that was really good.
Good. If you can master this,
Yes.
then everything else will kind of fit in.
Okay.
So this
practice
is
the rest
important.
of the ones.